Welcome back, and in this lecture we are going to talk about the principle of least action. And the goal of this is to get you, as you prepare to study QED, to sort of unshackle yourself from the idea that mechanics, right? This is basic mechanics, not continuum mechanics. Well, I guess it's all mechanics, right? Started from F equals ma, right? And Newton's, I guess this is his second law. Newton's second law has always been the origin of mechanics for us. This is the basic equation of motion for a free particle, right? And from this equation of motion, we have learned all of our elementary mechanics, and we're all interested in physics here, so we've all gone through this process of studying basic classical mechanics, and generally speaking, we start from this. And somewhere in this process, hopefully, you've learned about the Lagrangian. And the Lagrangian is presented to us, I think, generally speaking, the kinetic energy, which is often written as T, minus the potential energy. And this Lagrangian allows us, once we start using this Lagrangian, to develop the notion of Lagrangian mechanics, which is regular mechanics, but it starts from a very different place. It doesn't really start from F equals ma. Somehow you start with F equals ma, and then you arrive at this idea of the Lagrangian. And in particular, what you realize is that through the principle of least action, you can create a notion of the action, right? You can create a notion of the action, which is the Lagrangian, which is a function of coordinates, right? Q dot, and T. That should be familiar to you, what this all means, right? With respect to time. This idea, this notion of the action is important because the action is always minimized. And understanding, and we're going to go through what this all means in a moment to remind us, but this principle of minimizing the action associated with a given Lagrangian, which often, but not always, but often can be written in terms of the difference between the kinetic and the potential energy, somehow this process is what yields the equations of motion. It's not the other way around. It's not that the equation of motion teaches us about the Lagrangian, which teaches us about the principle of least action. We want to think of all of physics, almost all of physics, right, as starting from a principle of least action, which yields to us the equations of motion, right? And it's sort of the goal of this lecture to focus on that. So we are going to assume the principle of least action. That means we are going to say that for any physical system, we can formulate a complicated and interesting function called the Lagrangian. And when we integrate that Lagrangian between 2 points in time, that it will give us a number called the action. And that action will always be such that, well, let's put it this way. These coordinates will change as a function of time such that the action will be minimized. Already, this is like crazy hard compared to just F equals ma, which is, of course, why the historical development did not, in fact, start with the principle of least action. It was discovered. So we discovered through experiment and philosophy, just basic philosophy and experiment and, mathematical cleverness on the part of Newton, I suppose. We discovered this. And then from that, we kind of figured this out. I guess Hamilton was the guy who figured this out. And then at some point in the modern era, we realized, this is probably the most fundamental way of looking at mechanics. So let's start peeling this apart, getting down the principle of least action under our belts more solidly than it has been previously as a preparation for QED, where we will use the principle of least action extensively in our understanding of field theory. So let's begin by making sure we have a very solid understanding of every little aspect of this structure here. And we have to begin with these guys in the middle, these arguments of the Lagrangian. We have to know what the Lagrangian is which is a problem, but we have to know the Lagrangian is very largely defined by its arguments. So we need to understand what arguments we're playing with that describe the physical system. The Lagrangian is a function that is applied to arguments which are understood to somehow describe the physical system. And these arguments are called generalized coordinates. Now, in this particular integral for the action S, I've only put in one generalized coordinate and its associated generalized velocity and time explicitly. However, a physical system is generally more complicated than that and has multiple coordinates to describe the physical configuration of the system, and those coordinates all have multiple velocities. So just to give an example of some legendary examples here, if we look at this double pendulum, right, we might say that one coordinate is this angle, say we'll call it theta, off of the vertical of the first arm of the pendulum. And then the second arm of the pendulum, it'll have its own angle, which we might call psi, off of the vertical as well. And if I knew those two angles, I totally know the configuration of the system. What is the shape of the system? Now, obviously, those two angles are functions of time, right? That's the whole point. These generalized coordinates, all of them, all the Q's, are understood to be functions of time, which means that time ends up inside this Lagrangian in two separate ways. First, it ends up explicitly, but it also ends up implicitly through the fact that Q is a function of time and Q dot is a function of time, right? These are both understood to be functions. And so the argument of the Lagrangian are functions, right? And that is absolutely critical because that's what we want to find. We want to find those functions, right? If we're interested in this double pendulum, we're interested in how it moves in time. That's what physics is all about. That's what mechanics is all about. So we are looking for these functions, right? And the goal of this whole process is to get at what's sitting in the argument of the mysterious function that's in this integral, right? So now S is a number, right? Because L is going to be a function, and it's going to ultimately be a function of time. So when we integrate out time, then there's no variables left, and we get a number. So S is a number. So it's a number that depends on functions. And because of this, this is called a functional, right? And we can talk about the action functional. And that's what we're interested in calculating, is the action functional. So I've given this example. This is a really good example of multiple coordinates, although, for our review, we're not going to review all of Lagrangian mechanics. This is supposed to stimulate your memory, really. But it's also, I want to make sure, if this stuff wasn't clear the first time around, this is really critical. We're interested in these generalized coordinates as a function of time. Here's another good example of this. This one has three functions. This is a spinning top, right? So I've drawn this spinning top. And it's got three critical numbers that describe its configuration at any time. One is its angle relative to this z-axis. And then there's this angle here off of the z-axis as well. I guess this is relevant. I guess this angle phi is relative to, I suppose, this axis here, and this angle theta is relative to this axis here. These are supposed to be Euler angles. So okay, with an Euler angle, the first thing you do is you rotate around the z-axis, right? So this must be the z-axis. And then the second rotation for an Euler angle is around the x-axis. So that would be this guy, right? Now, since this axis would move here, then revolving around this would lower this angle. And then this last angle is around the new z-axis, right, phi. So this top is obviously sort of spinning around like this, but it's also precessing and things. And it has a center of mass, right? Center of mass is there, and so gravity is acting on it. Remember, this is a classic top problem. But the point is you have three coordinates, and they're all functions of time. You have theta as a function of time, you have phi as a function of time, and you have psi as a function of time. And this motion as a function of time, that's what's called precession, right? This thing precesses. And this is all supposed to be a poetic rhyme to our study of the magnetic field and precession and Larmor precession, not Larmor precession, but the Thomas precession, right? So the idea of precession, it's that's this guy as a function of time is the precession of this top. And this one actually shouldn't change as a function of time. That's going to be a constant of the motion. And then this guy, of course, is spinning the center mass motion around its central axis. So these are the generalized coordinates, and they have their generalized velocities, right? They have psi dot, phi dot, and theta dot, right? So that's the first thing to understand, is that these arguments are functions, and they're functions of time, and the Lagrangian is ultimately a function of time in that sense. However, we treat the independent variables as q, q dot, and t. So when we study the Lagrangian as a function, we will be taking its derivatives with respect to q and its derivatives with respect to q dot as though they're independent variables, unless we're taking total derivatives with respect to time, in which case we have to take a total derivative and we have to get in to these values of time. So that's the first thing to understand, is the Lagrangian is a function of functions, and ultimately time is at the bottom of the Lagrangian. Now, the other thing we should remember is your study for mechanics is that for most systems in classical non-relativistic mechanics, the Lagrangian is the kinetic energy minus the potential energy. So I need to take a system like this. I need to be able to use these coordinates to write the kinetic energy of the entire system. And in things like this is where the idea is, well, these links are massless, so the only mass is down here. Sometimes the links will have mass, in which case it gets to be a much trickier problem, but it can be done. The point is regardless of the mass of the links, the only coordinates you need are these two, phi and theta, for this double pendulum. And likewise for this top, right? At any given time, we can establish the kinetic energy of the top, the kinetic energy of rotation of the top, the potential energy of the top, because it's mass times a certain height, right? This center of mass has a height, so there's potential energy here. There's clearly potential energy wrapped up in the height of this blob, right? So the Lagrangian is just writing this down in terms of the generalized coordinates. And then once you have that, then you have something you can actually integrate. And then if you complete that integral from time t1 to t2, in principle, you could get the action. The problem is that to do this integral, you kind of need to know the answer, right? You need to know these functions of time to put into the Lagrangian in order to integrate with respect to time. And we can't do that, right? Because we don't know what these functions of time are. So even if we say, for example, that the kinetic energy or the potential energy, just say the potential energy is going to be, the height of this weight above a certain reference height. Well, I can express that height as a function of theta and as a function of theta and phi, but if I don't know theta of t and phi of t, I can't write down v as a function of time. And if I can't write it down as a function of time, I certainly can't integrate it. So that's really not how this is done, right? This is the point of this is we don't calculate the actual action in classical mechanics. We don't actually chug that number when we're learning it the way we normally learn it through the pedagogy. What we're studying is the principle of least action. And that's what we'll turn to next. Let's talk about though this. So it's the principle of least action that's important. That's what I'm trying to get at. It's not the ability to calculate the literal action of a physical system. Okay, so let's talk about that principle and how we can apply it and what it means now. So what you may remember from the study of the principle of least action in the past is this very important diagram that takes a generalized coordinate that stands in for every generalized coordinate, right? And time. Now time, when we talk about our integral, which I should write down, I'll just write down our integral again. It's important to understand that time is the time of some inertial frame. We are in an inertial frame of reference for the purposes of our discussions now. And whatever inertial frame you're in, that's the time. This is classical mechanics. This isn't relativistic yet. However, it's going to the same thing is going to be true for relativistic mechanics. The problem is the Lagrangian becomes a little more sophisticated. However, the idea that we present here is entirely universal to all relativistic and non-relativistic mechanics alike. But the idea is that Q is telling us the configuration of the system at any time. So at time t1, Q has a certain value. And then as time goes on, because Q is a function of time, Q is going to change. And it may change, say, like this. Say Q is a simple harmonic oscillator, right? And then it comes to time t2, and Q has a new value. And all through the intervening points, Q's value is changing. And this is the natural physical motion of our system. Say it's a simple harmonic oscillator, right? And if we knew what this function was, that would be the answer. That's the goal. That would be the resulting motion of the system with respect to time, at least for that one coordinate. So this is the true physical motion that nature decides is the appropriate motion for our, I don't know, I guess in this example I'm kind of stuck now with the spring mass system, you know, the classic where Q is the displacement of the mass from equilibrium, right? And Q dot is the velocity of the mass from equilibrium. So I'm sort of stuck with this little spring mass story, right? For the purposes of this graph, at least. So with that in mind, this is what nature does to solve the problem. And what we say is that there's a Lagrangian out there that describes this system or any system, and the path that nature chose is the path that when this function is substituted into the Lagrangian, you get the minimum value of S possible. That's the principle of least action, right? This is the action, and the path Q dot that the particle takes is such that this is minimized. And that's the fundamental principle, is that there is such a Lagrangian out there that does this, regardless of what Q and Q dot you use to define the system, right? It doesn't depend, if I construct the Lagrangian correctly for the appropriate, I choose Q and Q dot, and then I construct the appropriate Lagrangian. And then this integral is minimized for the correct path through time. So the idea is if this is a minimum, then any difference in path from Q is going to increase the value of S. So what we say is that if I added a little bit of coordinate value at every time to this true path, right, I would get a new path, which I would call Q hat of time. And Q hat of time differs from Q of time by a little bit at every time. And I can symbolize that in principle by drawing some other path that's sort of the same but not quite, right? It starts at a little different place, it ends at a little different place, and it's, it may cross every now and then, but it's arbitrarily different, right? The point is this new path is arbitrarily different. And I would kind of like to say that the action of this path is bigger than the action of the true path. Now, I can't quite say that the way I've drawn it, because it's very important that I'm talking about the same system. The path it takes, once it starts from this point and we let it go, the path it follows has to do at least two things. It has to, I'm interested in the path it follows from this point in time t1 to this point in time t2, and I'm expecting it to start and end at the same place. So this variation at the beginning and the end of the path has to be zero, right? So the path actually has to, one constraint that's really important is that the variation, well, I don't like the way this variation is. See, this variation is going backwards in time. I don't, I don't like that. So the variation has to begin and end at the same point, which means that del Q of t at t1 equals 0 and del Q of t at t2 equals 0. But it can actually be anything else in between. But we're going to constrain it to be small. And small always means that you can disregard its square, right? So we're now looking for variations on this path. And we're going to show that this integral, well, we're going to seek the conditions under which this integral is minimized. And that is the principle of least action. And there's this sort of canonical, ubiquitous analysis that every physicist has to memorize at some point in his life, his or her life, and we shall now do it. All right, so the idea is that this action integral is what we are minimizing. And the way we minimize it is we are seeking a path of the coordinate q of t and a path of the coordinate velocity q prime of t, such that when inserted into this mystery function, the Lagrangian, and integrated, we minimize s. Now, as I said, we're not going to actually calculate s. It's a little backwards, but we can talk about the quality that this minimum path must have, that these two functions must have, rules these two functions must obey. Well, specifically the equations of motion for these two functions that will make that happen. And so we are going to look for a variation of this path such that, well, we're looking for the path which, if it's varied a little bit, will not change the action integral because the action integral is a minimum. So the way we will look at this is we are going to create an alternative path, right? This is the path, this q of t, this is the path that nature chooses through space and time to solve the problem of motion for some physical system. But we're not going to consider that path. We're going to consider that natural path plus a little bit of a variation. So you can imagine that the coordinate value at some time t is a number. And then we add to that number a small amount given that that's described by a different function, delta q of t. And we do this for every single time. And delta q of t changes with time just like q of t does. So this represents a little deviation from the coordinate of the expected path. All right, that's what this is. That's that little red line. This makes up the little red line from the previous slide. And we're going to drop the functional dependence on time just for clarity because it is in there. Actually, this x, I don't want this x in here, right? The Lagrangian is not a function of space in our study. It is only a function of time, perhaps explicitly, and these coordinates, right? And so we're just going to write this as q plus delta q, understanding that everything is a function of time here. And so then the next part that we need to include here, is the fact that the true path at time t1, this is the initial state of the system. And our varied path, this is going to be called the varied path, this is the true path, and this is the variation, right? That's the language we'll use. Variation, true path, and q hat will be the varied path. But the position of the varied path and the position of the true path are the same at time t1, meaning that's the initial condition. And the variation at time t1 is therefore equal to 0. And the same is true for t2. Now, I think in the last slide I said the system has to begin and end at the same point. And that's not literally true. Q of t1 and Q of t2 don't have to be the same value of Q. What I meant is that the varied path has to have the same endpoints as the true path, right? That's what I meant on this other slide. Where's that other slide? Here. The varied path must have the same endpoints as the true path does. It's not, I think the language I said was the varied path and the true path have to begin and end at the same point. And And that would imply that somehow these 2 points are at the same location in Q or something. That's not the point. That's not the idea. The idea is that the varied path and the true path don't. There's no variation between the varied path and the true path at the endpoints of the motion. Okay, that's what I'm trying to say. So, so with these constraints in place, hey, just ignore this x. I can't erase it. Every time I undo something, it comes back. So just ignore that x for right now. The variation in the action, right, is the difference between the action you would calculate if you could calculate it for the varied path minus the action calculated for the true path. Now, if the true path is a minimum, then this variation is going to be zero even to first order, because this is a minimum. That's the way minimums work, right? You vary around the minimum and you don't really change much as long as the variation is extremely small, right? Is infinitesimal. So that's the plan right here. So I've got to write an expression for the action of the varied path minus the action of the true path. And that'll give me the variation in the action. And then I'm going to want to determine what circumstances make that variation zero. And I'm just going to write this down in the most obvious way. If I calculate the Lagrangian of the varied path and I subtract from it the action of if I calculate the action of the varied path and subtract from it the action of the true path, then that is the variation of the action, right? So what I'm going to actually do is I'm going to use a little bit of calculus to figure this out, because I'm going to say, well, I have the true path and I'm going to change it a little bit. And I want to figure out the difference that you get when you change it a little bit, and I'll call that the difference. And the way I write that is the variation in the true Lagrangian, right? Some variation in the true Lagrangian. If I make a variation and I'm going to get a variation in the true, if I make a variation in the paths, I'm going to get a variation of this integral. And that's going to be reflected by this difference. But remember, what I'm varying are the path and the velocities, right? I'm varying these variables, right? And I'm looking for a variation in the total integral. And the way that would work is I'm just looking for this difference. I guess the way I should put it is I should move this variation inside the integral and just calculate the variation of L. And the variation of L with respect to a change in these paths would be the partial derivative of L with respect to Q times the variation in Q, plus the partial derivative of L with respect to the other independent variable, Q dot, multiplied by the variation of Q dot, all integrated over dt. And that expression is just a way of expressing this difference, right? Given here the variation is wrapped up in these Q hats and Q dot hats. Here the variation is wrapped up in this variation symbol, which I can move inside the integral. And here I've actually kind of dispersed that variation into the literal things that we're actually varying, which is Q and Q dot. And we get this. And now, so this is kind of how the calculus of variation goes. The next step in this particular application, and this is the most general application, the principle of least action expressed in this way is like the first time you see calculus of variation in physics, that I remember. I mean, we did some work with like the calculation of, the shortest possible or the fastest possible wire connecting 2 points and things like that. I mean, there were some applications of calculus of variations, but this is the one where you're really making money. But the idea is there's a trick for getting Q dot, delta Q dot, converted into delta Q. And so you can pull that out of the integral. And that's sort of the inspired trick to make this work. And so let's look at that. The next step is to massage this term so that this guy goes away in favor of another instance of this cat. And I have written that down over here, right? This is the term we're interested in looking at closely. And what we're going to do is we're going to use integration by parts, right? And this is the integration by parts formula. It's got to sort of sit in your head. I scribbled it down here to remember how to do it so I could show you. But the integral of u dv equals uv minus the integral of v du. So with integration by parts, it's always a matter of figuring out what's u, what's v, what's du, and what's dv. And in this case, we're going to say u is this function, dl dq dot, and dv is this function, the variation of the velocity, the variation of the generalized velocity q, right? And that variation is actually, well, let me, this is not quite as good as it could be. It should be d by dt of del q, right? That's what, let's see, that's what this literally means, right? D by dt of del q. So if this is dv, then u times v is u times that integrated with respect to t, which is just the variation of q. And the integral of u dv is, or v du, right, is the derivative of this with respect to time. Now notice this is a total derivative here, right? This is d by dt. This is not a partial derivative. So you have to figure out what this guy is. If you know the Lagrangian as a function of q and q dot, you can take its derivative, partial derivative of the function of q as a function of q dot, but we're looking for the total derivative of this guy, right? And times the variation of the generalized coordinate. And then we have to understand that this, so I can now take this and substitute this right here. And when I do that, I have to remember that we're integrating, right? We're integrating. So, okay, wait, something's weird here. Okay, hold on a second. I'm getting a little careless. I'm missing a dt here for one thing, right? Right, this has to be dt, and because ultimately, and then, right, okay, so now it is an integration, so what we're doing is we're substituting in for, remember, we're after this integral t1 to t2 of partial L partial q dot del q dot dt, right? This is the piece that's actually under investigation, right? That's the left-hand side of our work. So when we do this, we end up with t1 to t2 of these, what this is called the boundary terms, right? These are the boundary terms, right? So, and then this is integrated from t1 to t2. Now, it's interesting, what is important about the boundary terms is that's exactly why I emphasize that the variation at the two boundaries is zero, right? You want to start and end at the same thing. So this whole term goes away. And all that's left is this piece right here. And this integral is what we're going to use to substitute right back into the integral for t1 to t2, partial L, partial q dot, variation of q dot dt. That becomes this guy. And when we do that, let's see, we go back over to here, and we're going to make the substitution right in here. And let's see, we'll get this expression right here. Now this is the integral, this is that total derivative, and I've pulled out the dt, and I've pulled out the del q's, the variations, which, and this now the variation of the velocity is gone, all in favor of this. Now that trick we just did with integration by parts happens all the time, and it's interpreted in different ways in different circumstances, but always keep that in your hip pocket. And then ultimately, this is the equation of motion, right? In order for this whole integral to be zero, which is what we're after, right? We are after delta s, and we want that to be zero. And in order for this to always be zero, since the variation is arbitrary, and where you start and where you finish is arbitrary, the only way this can ever be zero is if this expression is always true, meaning this term here, this middle thing has to always be 0. And that's the Euler-Lagrange equations. And so when you look at this, you realize, well, L, don't forget, right? L is a function of Q, which is a function of t, and Q dot, which is a function of t, and perhaps t itself, right? So this derivative is just a derivative of this with respect to an independent variable Q dot. This derivative is with respect to an independent variable Q. You can take the total derivative of this because everything is a function of t, so you can always take this total derivative. And in the end, this is an expression that's in terms of Q, Q dot, and t. And you set that equal to 0, it's a differential equation, and that differential equation, which is typically nonlinear in any interesting problem, but that differential equation is an equation of motion. All right, so that's our landing spot, is the Euler-Lagrange equation. So the principle of least action being fundamental, right, is this principle of least action being fundamental, or I guess this statement being fundamental, yields the equations of motion. So for a free particle, and we'll probably do this in our next lesson, we're going to do free particles, non-relativistic and relativistic, and maybe velocity-dependent forces as well, if we can fit it in to the next lesson. But this better end up giving us F equals ma, right? That better give us F equals ma. And likewise, it better give us F equals E charge times electric field plus V over C times magnetic field, right? Those are equations of motion, right? This is the equation of motion of a free particle. This is the equation of motion of a particle in an electromagnetic field. And we better be able to figure out a Lagrangian that gives us the correct force law for relativistic particles, right? This principle of least action is supposed to account for classical physics in all of its forms. I guess the real way to say it is, this is a true principle of nature. Well, nature is Lorentz invariant and relativistic. So it is a true principle that applies to relativistic circumstances, because that's the way the world is. The world is one big relativistic circumstance. So in the non-relativistic limit, I should get a Lagrangian that gives me F equals ma. And this should be true under all circumstances, because this, electromagnetism is supposed to be true. It's a relativistic process, which we have to come to study. That's another prerequisite that we're going to have to go through, is why is electromagnetism relativistic as is, and how do we force it to appear that way? And we're going to derive all of that from the principle of least actions, which is why we're going through this thorough review. And then there's one other thing about the Lagrangian that is our first step on a long and messy intellectual journey. And that comes down to these expressions I've written down right here. You can imagine that, say we figured out our Lagrangian for our physical system. Let's say it's that top, or that swinging pendulum, or a triple quadruple swinging pendulum on a top. It really doesn't matter. You can build a Lagrangian for almost anything. And imagine we just added some other function of position and time. And that function would contribute to the action through this little integral, right? The integral is linear, so we would have the original action plus this new piece, right? And that new piece is right here. But imagine if this capital H of the generalized coordinate in time was the total derivative of some other function, little h, of the generalized coordinate in time. In that case, this integral would be pretty easy to execute, because you would be integrating a total derivative over time, integrating it over time, and you would get this, and you would just get the difference of that little function little h, at time t2 and at time t1. So it would be the generalized coordinate at time t2 and the generalized coordinate at time t1. In fact, I probably should write this a little differently. I should probably write this q of t2, And likewise, this should be h of q of t1 at time t1, right? Something like that. The point is that these two things are numbers, right? They're just numbers. And you'll notice that if I varied the action, the only way Q shows up in here is through Q hat T2 and Q hat T1, right? If we did a variation of Q. But Q hat T1 and Q hat T2, as we've said a few times, are actually equal to Q T2 and Q T1. So the variation has no effect on this process. So these two numbers are the same for the true Lagrangian, the Lagrangian calculated using the true path, and the Lagrangian calculated using the varied path. And because of that, those two numbers would appear in this Lagrangian and in this Lagrangian in exactly the same way. And they would subtract off and be zero. The point is now your action is still zero. So these Lagrangians the Lagrangian with this extra function added onto it, if that a function was the total derivative of some other function, right? If you add a total derivative to the Lagrangian, a total derivative of time to the Lagrangian, you get the same equations of motion. So there's this redundancy in the Lagrangian. And these kinds of redundancies are really important in physics because they come up in so many different ways. And all of gauge theory is basically based on the concept of various redundancies that are part of physics, things that you can change that don't change the underlying physics. So it is important to keep in mind that if we add a total time derivative to the Lagrangian, then we won't actually change the Lagrangian at all. We won't actually change the equations of motion. The physics will remain the same. The Lagrangian changes by that total time derivative, by adding a total time derivative to it. So there's one last thing we want to cover before we move on. Let's look at our principle of least action, which is saying that this action integral is a minimum for this particular motion here, which I've gotten as T1, T2. T1 and T2 are arbitrary, and so this is going to be finite. And you might sort of dive in a little bit to the philosophy of physics and ask yourself, well, wait a minute, how does a mass know what's going to happen in the future? Something might happen in the middle between T1 and T2 that would disrupt this and change the path, right? Maybe a force will suddenly get applied that the particle, that there's no reason to expect. Unless, you might be able to say, well, look, it's a block universe. The future's determined. So this is all established. You might go down some route like that. Or you might say, well, that's a good point. We really want our laws of physics only to be true to be sort of differential laws of physics, right? Everything has to be super local. This is not a local law of physics because it depends on things that happen at different times, right? Local laws of physics have to happen right at one point. So F equals ma, that's a good example of a local law of physics. At any instant of time, a force will drive an acceleration that's proportional to the mass, right? So and then that process integrated through time produces this line, right? And that's a legitimate way of looking at physics. And the question is, well, all right, this is neither here nor there. They're all equivalent. But I am asking you to sort of take the principle of least action as the primary law, which kind of opens us up to this question a little bit at least. And there actually is a nice way to get through that issue. And the way to do it is to realize, of course, that this T2 is arbitrary and that I can take this point to be anywhere in this process or any time in the future. And the principle of least action holds in all of these intervals of time. And I can go all the way back to some time that's very close to the initial time. And in fact, I can get so close to the initial time that the motion is really a straight line, right? I'll just draw this straight line motion. And the principle of least action applies there, right? Del S equals 0 for this motion, just like it did for the total motion. In fact, you could argue, well, it's the same thing, right? It's just a shorter time interval. But the difference here is that I can always get so close to the initial point that this is a straight line. And the reason that's important is because if that's the case, then my Lagrangian suddenly really doesn't depend on Q double dot, Q triple dot, right? And all these other higher derivatives of Q, right? Because if they did, if it was substantial, then we're dealing with, when we construct the Lagrangian, if these things are part of it, this path isn't going to be straight, right? And in this configuration space, right? And so this is the explanation, first of all, of why we can look at the action principle as sort of an infinitesimal principle too, right? Because we can shrink it down to these infinitesimal units. So it becomes just as good as F equals ma. But it also tells us why these terms are not included in the Lagrangian, right? Because if they were, then you would have trouble down here where the path is only dependent on the position and the velocity, or the path through configuration space is straight. So that's sort of an important thing. A little philosophical excursion, but I think it's pretty interesting. And I didn't explain earlier why these derivatives weren't present. And this argument is actually pretty solid. I mean, you can make this quite formal and see that those derivatives don't belong there. Or if they do, you start getting things that are really haywire. You can get things that go backwards in time and all kinds of crazy stuff. And you get all these initial conditions that become very, very difficult to articulate and difficult to specify and cause real problems with the theory. Okay, so there we are done with this. Now our next step is going to be to take the principle of least action, and we're going to just apply it in a rudimentary way. By the way, if you haven't done Lagrangian mechanics and studied problems like the spinning top and the double pendulum and the double pendulum with a springy top or things like that, and calculated the nonlinear equations of motion for those things, and done things like non-conservative forces, you really should. I mean, I don't know if that's a literal prerequisite for the class, but it really would help you understand all this. But we are going to apply this in our next lesson to a free particle, relativistic and non-relativistic, and then we're going to start applying it to the electromagnetism. We're going to figure out a way to understand the electromagnetic field using the principle of least action, because it applies. If you can if it's a physical system, you should be able to build a Lagrangian, and we're going to introduce electromagnetism that way, and that's going to set us up to understand the Lorentz invariance of electromagnetism, and it's going to get us to understand ultimately the Lagrangian for field theories, which is going to lead into the ability to quantize, and that's why this is all prerequisite material. Okay, see you next time.